Yeah, thank you. So thanks to organizers, Anki and James, and I really enjoying this workshop. Today I'm going to talk about our recent work that we use nonlinear phononics that you've heard from Nicole and Anki's talk to control ferroelectricity and antiferric magnetism at the same time. So give you two examples as introduction what nonlinear phononics has been applied in a material system. So first example is here. So we chose this bilayer cuprate YbCl, and in this material that you see here is apical oxygen. So this apical oxygen distance from this apical oxygen to the copper oxide plane is very critical for the superconducting properties. So we generate high intense mid-IR driving pulse, and we tune it to resonantly excite this apical oxygen phonon. In this way, we can modulate the distance of this apical oxygen to the copper oxide plane. And a serious work has been done here. So what we saw is in the high temperature phase, that we saw along the c-axis of YbCl, we saw a superconducting-like transient plasma edge and emerges. And this appears in various underdoped samples and then disappears at omnidoped samples. So this is applied nonlinear phononics to superconductors. And the second set of example is Tobias and Ankit did this pioneering work that they chose STO, and they use intense mid-infrared pulse to drive the highest energy IR active mode. And then they saw a very long-lived ferroelectric state emerge, although then the mid-IR pulse was already passed, so the system still remained in the ferroelectric phase. So this is a set of examples showing you nonlinear phononics is a very powerful tool that we can dynamically engineer materials properties. So today I'm going to focus on using nonlinear phononics to control ferroelectrics. This is initiated by Alaska Subidi's prediction that he studied lead titanate, and he found there's a strong QIR square QR coupling that you saw from this morning Nicole's talk. So basically, this high energy IR mode couples strongly to the low energy ferroelectric mode. And by driving the high energy IR mode, Alaska predict there can be an ultra-fast ferroelectric switching, and which is also long-lasting. So the result is shown here. This is the coordinate of the IR mode that you are driving. And it couples to the Raman mode, which distort along this QP is a coordinate for this low energy ferroelectric mode. So in the equilibrium, so when you don't drive the IR mode, the system is ferroelectric. And when you drive the IR coordinate to a different amplitude, you see that the free energy already start to, so here it already start to move slightly towards negative QP. So here in his convention, he says this negative QP would reverse the polarization. So when you drive the IR coordinate to large amplitude and positive, and then you see the free energy curve has the minimum, which is corresponding to a very large number of QP. So the system would flip ferroelectric polarization once you drive the high energy IR phonon. So this is a very interesting prediction, and there is a pioneering experimental work done by Roman Mankowski, where he chose the system is lithium niobate. It's a very classic nonlinear crystal. So lithium niobate is ferroelectric at room temperature. We can view this ferroelectric coming from, you see this cations is moving off center of this octahedra, and here this cation also move out of the oxygen plane. So they have from lithium and niobate the contribution of polarization along the same c-axis direction. So here is the optical reflectivity where you see two phonons. So here this high energy phonon around 20 terahertz correspond to the phonon in that Titan and Alaska predict. When you drive this phonon, it will couple to this low energy ferroelectric mode to achieve the ferroelectric switching. So here is an experiment where Roman used this strong field mid-IR pulse to drive this 20 terahertz IR active phonon. And then he measured second harmonic generation intensity, which is reflecting the second harmonic polarization. And he saw before the mid-IR pulse arrives, let's say you have a net polarization along the positive direction. And once you shine the mid-IR pulse, you will see the polarization flip 180 degrees. And it is unfortunately not long-lasting. So shortly after the mid-IR pulse is gone, the ferroelectric polarization switch back. But interestingly, as Alaska predicted, this ferroelectric switching is bidirectional. So if you start from a ferroelectric polarization at equilibrium is pointing down, and you shine the same mid-IR pulse, and then you can do the same 180 ferroelectric switching. So this is a very interesting experiment, which I really inspired me. So I would like to explore more along this direction. What can we do, nonlinear phononics, to control ferroelectricity? First, are there other materials we can achieve this ferroelectric switching? And can we have some input about this lifetime of the state and so on? So the material I chose to study is this bismuth ferrite. There are multiple reasons. First, because it's a very strong ferroelectric material. At room temperature, it's ferroelectric. So the Curie temperature is 850 degrees Celsius. And at the same time, the interesting point, I think, is this antiferromagnetic ordering. So at room temperature, bismuth ferrite is also antiferromagnetic. So then my thought is, can we, by using nonlinear phononics, distort the lattice structure, control ferroelectricity, and also at the same time, can we control antiferromagnetism? Because if we can do that, it would be very energy efficient. You use electric field to control antiferromagnetism. So the magnetic structure of bismuth ferrite is a little bit complicated. So the spin on this iron side is antiferromagnetic order in one unit cell, but then it's a little bit canted, so it has a net spin pointing. And then if you explore away from this unit cell, so along the direction, so this I forgot to say, so one of the body diagonal direction is a ferroelectric polarization direction. So this is rhombohedral, and it has 3 mirror planes. Along one of the direction of this mirror plane orientation, this canted spin actually rotates. So it has a cycloid, very long range, 62 nanometer of this spin period. So because these unit cells, neighboring unit cells, have this long cycloid rotation, so that means when you develop this antiferromagnetic ordering, you actually break the 3-fold rotation around the ferroelectric polarization. So now in the antiferromagnetic state, the system can take tau 1, tau 2, or tau 3. They are 120 degrees in between. So then, which means you break the 3-fold rotational symmetry around P. So this will be very important in our data analysis. Okay, so because we want to do this nonlinear phononics, we need a very well-defined crystal orientation, so that we need a single crystal, so that in this crystal area, we can be sure that this direction is uniform. You drive the mid-IR polarized along this ferroelectric direction, and you can control the material's property. So here is a crystal we chose this 110 pseudocubic orientation, because then this 111 direction lies in plane. So we then shine the mid-IR electric field is polarized in plane, so we can drive the high energy A1 phonon. So here, this is like a cartoon showing you the result. What we observe in the end is actually we control, so this is mid-IR pulse. We go to drive this A1G phonon, and we distort the lattice such that we control the ferroelectricity. And at the same time, we actually also control the antiferromagnetism. That at room temperature, you can think there's thermal fluctuation of the spins. And once we shine a mid-IR pulse on, it actually stabilizes, so there's less spin fluctuation. We actually enhance antiferromagnetic signal. So now I'm going to explain you in details how we discover that. So bismuth ferrite has a very strong second-order optical nonlinearity. So we make use of that, that when you shine, say, a single frequency light on, we use this 800 nanometer to probe. And then this very strong Chi2 effect will induce two nonlinear effects, which is you can have the frequency doubling, we call this second harmonic generation, and you can also have this zero frequency component generate, which is actually terahertz emission. So by detecting the terahertz emission, we kind of verify the ferroelectric polarization, and by detect the second harmonic generation, we check how the system change symmetry in the light-driven state. So first, I'm going to show you this terahertz emission experiment. So this is kind of equilibrium measurement. There's no mid-IR pumping. In this experiment, we rotate the crystal orientation around the surface normal, and we shine in a linearly polarized 800 nanometer in, and it will generate terahertz emission. And then we measure along a fixed direction polarization, we measure the terahertz field. And then while we're rotating the crystal, whenever the ferroelectric polarization is parallel to the in-plane projection of your incoming electric field, we see a large terahertz peak fields. So which is kind of an evidence verify that this material is mostly single domain. I mean, we did X-ray beforehand. But in order to carefully orient the sample for the mid-IR pumping, we need to characterize the exact orientation of ferroelectric polarization. So here is you see with several rotational angle of the sample, this is a generated terahertz magnitude, and it indeed follows a very well-defined angle dependence, which says our material is mostly a single domain. Okay, so then in the pump probe measurement, we shine the mid-IR pump. The frequency is tuned to this high energy IR active phonon, and the polarization is tuned to be parallel to the ferroelectric polarization direction. And then we measure the second harmonic generation intensity along the parallel direction, which is defined as P here. So when we shine the mid-IR pulse here, and we measure the light-induced change in the second harmonic generation intensity along this direction, and we see the second harmonic generation signal enhances. And so if you remember what I told you earlier, the Roman-Minkowski's ferroelectric switching, when they drive the mid-IR phonon at high frequency, they saw a flipping of the second harmonic generation signal, so they saw switching. What we see here is we see an enhance of the second harmonic generation intensity, which is different to their result. So to verify whether it's really a phonon-driven effect, we then flip the orientation of the mid-IR pump field. So now it's not, although the frequency is the same as the high IR frequency, but it's orthogonal to the phonon resonant direction, so you would not excite any IR phonon. And in that case, indeed, we saw zero change of the second harmonic generation intensity. So to further verify that we indeed saw the phonon-driven effect, we tune the frequency of this mid-IR pump field to be off resonance. So the phonon of this high-energy A1 phonon is more or less close to 69 millieV. So we can do higher energy away from this driven phonon, the phonon we want to drive. And we see that whenever we tune the frequency of the driving field away from the phonon, the effect of the second harmonic generation intensity quickly dies away. So another evidence to show that indeed a nonlinear phononics effect is then we change the pump fluence of the mid-IR. And we'll see it's now I'm changing, so it's not the intensity, but it's the second harmonic polarization. So the polarization scale linearly with the pump fluence, so which means the polarization scale square with the electric field, which verifies indeed we are driving with this QIR square, QR type of coupling. Okay, so this tells us the effect we saw is indeed phonon-driven. And then we want to understand what happens to the symmetry in this light-driven state. To understand that, we first have to understand the second harmonic generation signal at equilibrium. So here, the second harmonic polarization is determined by this Chi2 term. This is a tensor. And this tensor has this form. And for the ferroelectric bismuth ferrite, it actually has two components. So this is from the ferroelectric contribution, and this is from the antiferromagnetic contribution. So this reflects the symmetry of the material. So for the ferroelectric part, is determined by the structure that it has a point group 3M. So we have 4 independent non-zero SSG tensor. And because this material is also a single tau magnetic domain, so as I said, it breaks the 3-fold rotation around P. So you can imagine the antiferromagnetism must further break down the symmetry of this structural point group, that you will have more non-zero SSG tensors. So that means when you measure the SSG, you will see different shape of flowers coming from the ferroelectric contribution and coming from the antiferromagnetic contribution. So using second harmonic generation as a sensitive tool to detect antiferromagnetism has been done in this bismuth ferrite. It's very nice work. So they studied the bismuth ferrite thin film, and in the antiferromagnetic state, they saw this is the second harmonic generation signal, and they break it down to 2 components. The gray component is from the ferroelectric contribution, and here the white component is from antiferromagnetic contribution. So here they are studying a thin film where they know this material has multiple domains, and they know there are different antiferromagnetic orientation. So then they can exactly measure this from the SSG. So it's very powerful, where you see this flower is a little bit asymmetric along this direction, which correspond to one antiferromagnetic domain, and then when it's asymmetric along that direction, is another antiferromagnetic domain. So here is the second harmonic generation equilibrium for our single domain crystal, and we indeed can reproduce what the previous discovery, that along, so this is along a P direction probe, this is along S direction probe, where you see the similar structure as previous work have seen, that this flower has a little bit asymmetry along this 60 degree and 240 degrees. This is the red part is from the AFM contribution. And for the orthogonal direction probe, we see majority is from the ferroelectric contribution. Okay, so with this in mind, now we shine a mid-IR pulse on and see what happens to the symmetry of the SSG flowers. Here I start from the S probe. So to remind you, this is the antiferromagnetic contribution. And in the light-driven state, the data can be fit very well with a very large contribution from the AFM, and a small gray part is from the ferroelectric contribution. So the nice thing about SSG is you can measure these 2 orthogonal directions, which reflect the SSG tensors from a different perspective. And then we measure the orthogonal direction probe, and this is the equilibrium to remind you. And here is the light-induced change. You see it's mostly can be fitted with a large contribution from the ferroelectric tensors. So by fitting the S and P polarizations together, we get a conclusion that both, so if I go back, so both the antiferromagnetic contribution and the ferroelectric contribution, they are enhanced. And to understand what exactly happened to the structure, we collaborate with Dominic Schwarzek and Michael Fashner. So they did a first principle calculation, and in the phonon-driven state, they considered the coupling of the high energy A1 mode we drive to all the low energy modes. And then they predict how each atom is going to distort in the pump-induced state. And very interestingly, if you remember, I said it's lithium niobate, so the polarization of this lithium and niobate contribution, they are aligned along the same direction. Here, similar for bismuth ferrite, so the ferroelectric polarization contribute from bismuth and iron. They are both along the 111 direction. And in the driven state, this is what you see, this darker color. All these atoms displaced from the equilibrium position, which is this shading color. And interestingly, you see this bismuth is moving opposite direction of the equilibrium polarization, and the iron is moving along the equilibrium polarization. So with this, it's very straightforward. You see why this case is different to the lithium niobate case, where both atoms move along the same direction, and here, although we are driving a similar high energy phonon, you cancel the ferroelectric polarization by quite a lot. So here is the details. They consider the driven phonon coupled to all these low energy phonons, and each phonon's contribution to ferroelectric polarization. And you see, indeed, there are some enhance of ferroelectric polarization, but also there's a very, very large negative contribution. So in the end, in total, we have a very small enhancement of the ferroelectric polarization, which actually agree with experimental result. And then they also predict the second harmonic generation, this flower. And this prediction is based on, so now they only calculate the distorted lattice, so that is only the ferroelectric contribution. Now you should only compare this theory result with our measurement, only the gray part from the feet. So you see a theory very well reproduce our experimental result that along the p direction, you should see this 2-lobe signal, and along the s direction probe, you should see this nearly 4-lobe signal, and the magnitude it also nicely fits the experimental the observation. So what theory cannot, at the moment, is not calculated is the antiferromagnetic, that contribution to the SSG is complicated because you need more unit cells to mimic this very long range of antiferromagnetic cycloid order. So, okay, so with this, I'm going to summarize our work. We use nonlinear phononics that we shine a very strong mid-IR pump on this multiferroic bismuth ferrite, and we saw an enhance of the second harmonic generation signal, which signify the enhance of ferroelectricity, and very interesting, the enhance of antiferromagnetic signal. So our conclusion is we can use mid-IR light field to control ferroelectricity and antiferromagnetic order at the same time. Okay, so this work involves contribution from my student Daniel. He did data analysis, and a sample, very nice single domain sample is critical, is from Sang-Woo Chong's group from Rutgers, and theory calculations from Dominique Chuarek and Michael Fashner from Max Planck, and the funding is from DOE, and work at Rutgers also funded by Keck Foundation. And with that, I would like to thank you for your attention.